and welcome to the Planning Analytics Deep Dive. I'm Andrew, and I'm joined today by my colleagues Steve and Alex, and we're here to talk to you about a couple fun things, and Alex has got some stuff to share with you all.
Thanks, Andrew. Yeah, I'm excited to hear about this, Alex. I hear you got some pretty cool stuff for us to see and talk about today.
Yeah, I've recently had an opportunity to deep dive into some decision optimization, and I've learned a lot, and there's some really cool stuff that you can build out of it. First, I would like to show Sudoku and how decision optimization could solve a puzzle for you. Anybody want to race
Nice.
me?
So, Alex, maybe you can just start for the audience and let them know like what is decision optimization.
Decision optimization is a mathematical algorithm that can be used to solve problems for you. So, if you are trying to do things like how many items can I package into a truck? How many items can I fit in a truck? Or how many items can I produce on a single production line? Just decision optimization could solve that problem for you. Take all the thinking out of it and let the computer do the thinking for you.
Yeah, I remember kind of like, harkening back to my grad school days doing like linear programming and stuff in Excel, optimizing, maximizing, minimizing, that kind of stuff, similar, right?
Yeah, exactly. Linear programming, and you could set a problem to maximize or minimize. You want to minimize cost, or you want to maximize the amount of items you can produce. Linear programming and decision optimization could solve that for you.
So,
Nice.
so you mentioned something about Sudoku. I'm really interested in this. My wife loves Sudoku, so I'm going to be like her favorite person in the world. So, can you show us?
Yeah, definitely. Let's jump right in. Let me go
Awesome.
ahead and share my screen.
Oh,
All right.
cool.
So on the screen, you should see a basic interface. This is built in PA that will show a Sudoku puzzle and different selections you can make. So you can choose between an easy, medium, or hard puzzle, and we can load it directly from New York Times. So it this process will scrape the puzzles off of the New York Times Sudokus, whatever's set for the day, and then from there you can go ahead and solve the problem.
So, hang on a
So
second. I just pause there for a second. I'm really interested. You said this is in paw. So, is this a cube view?
yes, so on your right here with titled Sudoku, this is exactly a cube view. So each one of these little boxes are little squares
Planning analytics, the
themselves.
next game engine, guys.
Yeah, I know, right? Yeah, this is really cool. I haven't been able to make things that look exactly like this in Workspace. So it's just an exploration. You must have done some conditional formatting, added some, tricks in here. Looks really nice.
Yep, Planning Analytics Workspace has a lot of flexibility and a lot of neat things you can do with it.
All right, now to the decision optimization. Sorry, I didn't want to get distracted by pretty workspace.
All right, so you'll notice I already have the puzzle preloaded. In case it wasn't for you, you can go ahead and preload the puzzle just by clicking this button. This will run some Python in the background that will load the puzzle in, and it will load it directly into input. So we have three selections. We'll start with the easy one. From here, we can go ahead and solve the puzzle. So I'll give you a couple seconds to try and solve the puzzle, and then maybe I'll race you. All right,
Uh,
enough waiting.
yeah.
I am going to go ahead and click the button, and we'll see what our solutions are. And so you'll see in the upper right hand corner, pop-up message said that it was complete. So we'll hop into our first solve. And you'll notice that Sudoku solved for you. So Steve, you can race your wife, and you can beat her in seconds.
Absolutely, I'm betting on this now.
Sudokus, if they're formed really well, you generally will have one solve, but sometimes you can have more than one solve. So one of the cool features I added into this decision optimization or this problem was the ability to recognize, hey, there's an additional solve. Let's go back and make an additional solve. Not really likely, so you'll see this is all zeros because I'm sure New York Times has some great puzzles, but it is just an example of what you can do with decision optimization.
So, Alex,
That's
this
really
is
cool.
really cool. Can you maybe take us through like how you're actually doing this, like the nuts and the bolts? I mean, do you have code you can show us?
Yeah, absolutely. Let me get that open for you.
Nice. Yeah, don't just show it to us. Prove it to us.
Yeah. Okay. Hopefully you can see my screen here. I've got the solver pulled up. First thing you're going to want to do is pull in a few libraries. Now, I myself like using the pulp library. So that's a library dedicated just for linear programming. One of the unique features about pulp that I like is, one, it makes it very easy to set up your problem. And two, it will identify the best solver for your problem and the most efficient solver for your problem and use that to solve it. So I will move through this the script. The top part is just some parameters that I set up. Some of it not all that relevant. And I will move into the first piece that's important here. So I am logging into TM1 here, and I am setting up a query. So this is define TM1 query. And I am pulling the data directly out of TM1. So it's from this input. You'll see this input here. So that's what is loaded directly from New York Times. And so I'm pulling the Sudoku puzzle, what's unsolved, and bringing that in. Next, you'll see I have some variable set up. So I am passing in the puzzle as a parameter. So if you remember back on the original screen, I had an easy, a medium, and hard puzzle. You can select that puzzle and bring that in. And then I'm setting up a few static variables, so a sequence. So as you know, in a Sudoku, you want to solve 1 through 9 in all the little boxes, and all the rows, and all the columns.
Okay, so is this really your defining the rules of your decision optimization?
This is just defining the variables.
Gotcha.
And the variables are really important because setting up the variables is used for constraints. So constraining your problem in order to solve it. So here we have our values. So the way this problem is set up is a little unique. Instead of solving for a number, we're solving that a number is filled out. So for each value 1 through 9, for each row 1 through 9, and each column 1 through 9. In addition, we also want to do the same for boxes. So here I'm setting up tuples that will say for the combination of the row and column, is that filled out for the numbers 1 through 9. And I'll go into a little more detail later in those constraints. One of the first steps to setting up your problem is setting up your problem variable. And the problem variable for pulp will contain all the problem data and all the constraints used to solve the problem. So I used a minimize here. The way this problem is set up, it doesn't matter if it's a maximize or minimize. I just want to make sure it's solved. And then I'm setting up one variable, so choices. So we want to. Sorry, one sec.
It's okay. If it's easier, Alex, I don't think you need to go through every line, right? You can more jump to the broader things here and level it up a little bit to describe the cool stuff. And because the other thing that we got to talk about after this is how this applies to the real world as well. So,
okay.
Mm-hmm.
Okay, so jumping directly into the problem. In order to set up the problem, you got to set up a couple variables. So you set up the first problem variable, and then any of the constraints, the variables that are used for your constraints. So choices is an example. And then with linear programming, you have to set up your objective function. Here, it doesn't matter. We are just solving for, is the square filled out for that combination? So we have 4 constraints in total. The first one will show that will ensure that one value is in each square. So every square in the rows and columns will have a value. The second constraint is actually a few of them, is for each value in the rows has a value, for each column has a value, and then each of the boxes has a value. Now, if you remember, the number we want is the V. So we want to make sure that when it's solved for that 1b. And then finally, the third constraint is the starting numbers. So we want to identify what the starting numbers already are, because we don't want that number to be repeated anywhere. So in the row where we have a 9 already, we don't want another 9 showing up. So we do that here for the rows and columns, and for the values too, or the boxes. So this is adding them in, and finally we can go ahead and solve it. So I set this in a loop because if you remember earlier, we have an additional constraint in there. If a Sudoku puzzle could be solved multiple times, we want to be able to build on that problem. So here's the statement where we solve the problem. Pulp uses its choice solver and will return a status. So if the problem is solved, you'll get a successful status, and we can take those values and bring them back into TM1.
Nice. So, I mean, I like that you chose pulp for this too, because it does lay it out pretty well, right? You define your variables, you put in some constraints, you define the problem, whether you're maximizing, minimizing, you define your objective, and then you just solve, right?
Yes.
And it goes right here and then load it back to TM1. So, yeah, this is pretty powerful. And obviously you can imagine how you could, take this and run with it in all kinds of planning analytics scenarios, different planning analytics data, and or beat your wife in Sudoku.
Yeah, exactly. It's just that easy.
Exactly. And I mean, Alex, do you have an example of using this at a project or with a customer?
Yeah, I was just with a customer where we used it to balance inventory across different warehouses. So this use case was trying to maximize their days of supply for a group of warehouses, and that may include pulling inventory from one warehouse and bringing it into another warehouse so that they're even across the board. By maximizing it for that entire group, we'll maximize the days of supply for the company. So
that sounds pretty awesome. I mean, I guess that's and I know you mentioned the one around sort of trucks earlier and being able to like optimize the space in trucks or something along those lines that you referred to. Are there other, I mean, obviously you have this great example of this project you were just on, but are there other things you've thought of that maybe, ways to apply the same technology?
Yeah, there are a number of ways we can use this, and you can get really creative and complex with it, which is the fun in this. So one good example is setting up your routes. So for if you want to minimize the cost it takes to transport goods between, say, a manufacturing plant to a distribution center, you can minimize the cost that it takes to do that. So by saying this is the number of miles that we need to transport the goods, this is the amount it costs to move the goods that amount of miles, we could reduce the number of trucks that we're moving across the country.
Well, Alex, this has been really, really great. Thank you for taking us through this. It seems like there's a lot of potential here for this stuff. So great conversation. That code is really cool, using pulp and TM1 Pi to be able to do some of this stuff. Really creative use case, and I'm excited to see more of this.
Yeah, fun stuff too. Appreciate you coming on, and thanks everybody for joining us on another Planning Analytics deep dive. More to come in this space soon.